Right, so let's do number 4 in chapter 10 here. And this has from here, and it's asking you, how do we get to here? I know it shows you 2 boxes here, but I wanted to make sure we practice retrosynthetic analysis, right? Don't worry about the boxes. Worry about going from the final product to the starting material. Right? So when we work backwards, right? So here we have an alkene, right? And matter of fact, we have an alkene that's the most substitute alkene, right? Where would this come from? So let's number our carbons: 1, 2, 3, 4, 5, 6, 7. What starting materials make alkenes? We've been doing all these eliminations. What are the starting materials? What kind of starting materials are they? Bulky base is the reagent usually that helps do the elimination, but what's the actual other starting material? What do we call that? The alkyl halide, right? So if we have an alkyl halide here, where do we want to put the halide? On which carbon? We can put it on 3, but then you should also be cognizant of what you're trying to make here, right? So if you're going to put something on, right, at the end of the day, you want to start with a double bond here, right? So I would start thinking, I want to keep stuff, the action, whatever I'm doing, I want to keep it between carbon 2 and 7. So yes, you could put an alkyl halide at 3, right? But then you'd also get a mixture of products, right? It'd be possible to form a double bond here, right? Or double bond here. So, and plus, since you know the starting material, I would put the halide on which carbon do you think? I would put it on 2, right? The more substituted one, right? Not 7 just yet, on 2. Right, because if the alkyl halide was on 7, is there a way to make a double bond between 2 and 3? No. So the alkyl halide either has to be on carbon 2 or carbon 3 of the double bond. It can't be on 7. Right, I chose 2 because 2 still has a pi bond on it in the starting material. All right. So we're saying tertiary alkyl halide, and we already know that's really good for eliminations anyways, E2 or E1, right? A tertiary alkyl halide is a good thing. 2, 7, 3, 4, 5, 6. How do we make a tertiary alkyl halide? What can we make that from? How do I add one? So the reagent I would use is HBr, but what's the starting material I'd use? An alkene, a double bond. So where would the double bond have to be to get the bromine to add on carbon 2? Between 2 and 7, right? And that's back to what we want to get to, right? So you see this this is a rigmarole, right? So this is a common sequence of events where you have a double bond, an alkene, that's not the most substituted. But if you do a series of reactions, you can get it inside or be more substituted. Right? So the first step, what are we going to do here? What reagents are we going to use? We take the alkene between 2 and 7 and add a bromine. What reagents are we using here? HBr, right? So the one thing people forget, we formed a bond between carbon 2 and the bromine. What other bond did we form in this reaction? H to which carbon? 7, right? There's also a new CH bond here. That's right. What reagents do we need to do this next step? So this was an addition reaction when we added HBr in the first step. In the second step, what kind of reaction are we going to do? An elimination. So what do we need to use? A base, a bulky base if we can. But I don't think we want to use a super bulky base, right? So remember we learned about today about the non-Zaitsev product. This product is what? This is a Zaitsev product, right? More substituted. So if I use a really bulky base, I would end up getting the non-Zaitsev product. That's not what I want. So I can't use a super bulky base. So the example they have is the ethoxide. Right? Because can I do an SN2 on a tertiary alkyl halide ever? So I don't even need to worry about SN2. But I don't want to use too big of a base here, otherwise I'd get the alkene here, and I want it here. So those are the 2 reagents you'd want to use. All right, taking a look at number 7. right? And they're reacting this with so this is tert-butoxide and tert-butanol. So another way we could write this is just like this. Right? Same thing. So something you've seen before but maybe written in a different way. So the first thing we ask ourselves is what type of alkyl halide do we have here? What type do we have? How many carbons is this alkyl halide? This carbon right here. Secondary alkyl halide. So we could still do SN2 or E2. Can we do E1 or SN1? No. So if it's just secondary, we can't. So then we look at our nucleophile or base. It's reactive, but is it big or small? Big. So SN2 probably seems less likely. And in this case, we got to find, right, what are the possible products. So they're actually saying one major product. I would say there's probably two major products, right? What people are probably going to do, so the first thing you look at, it's an E2 reaction. What do you need to look for? Look for antiperiplanar and also beta hydrogens, right? So if this is our alpha carbon, there's beta H's on this methyl, and there's beta H's here. So how many types of beta hydrogens are there? Two. So there's two possible products then, right? If I number these carbons, 1, 2, 3, 4, 5, 6. This is a pretty bulky base, so I would go with probably the major one is probably going to be the beta hydrogens off of carbon 1. So it's kind of a setup, right? They have it all lined up, antiperiplanar, and then you're not going to do the elimination there. In reality, if you wrote that on the test, you could have both. Both products are probably likely. I would say they should have both products here, not just the one. But don't forsake the non-Zaitsev product here, right? Bulky base, even if it's secondary. So, say there's 3 H's here. Let's say the H. So the new pi bonds between which two carbons? 1 and 2. So nothing happened at carbon 3, so that stereochemistry just stays the same. One, 2, 3, 4, 5, 6. So this is a non-Zaitsev product, right? Bulky base. Secondary alkyl halide still pretty hindered, but I would also say another product you could draw, which most people probably did right away, is this. Now, so I would think this product is fine too. 1, 2, 3, 4, 5, 6. Notice, are there any wedges and hatches on carbon 2 and 3? No. Wedges and hatches do not belong on sp2 hybridized carbons. I don't care if sapling says it's okay. It's not okay. No wedges and hatches on sp2 hybridized carbons. No wedges and hatches. They help us understand, right, that these two methyls are on the same side, that H and the ethyl are on the same side. Right? So I think they want just this answer, but I would think both products are going to happen. You're going to form both products. Both E2 reactions, right? Both E2 reactions. So it's not that the non-Zaitsev product is the only, I disagree. It's not the only one formed. I would say you'd have a mixture of both the non-Zaitsev and the Zaitsev. Normally I would say it has to be tertiary alkyl halide and a bulky base. It has to be both those things for this to really happen. Okay, let's look at number 16 in chapter 10. Looks like we're going to have a chlorine here. We have an ethyl. So we have an H and an H, right? So there's a bunch of other CHs in there as well, but I'm not going to mess around too much with that for right now. So we have OH minus, DMSO, which is a polar aprotic solvent. Right, DMSO. Dimethyl sulfoxide. So if we see something in a 6-member ring like this, we want to get our leaving group to be we need it to be an anti-periplanetary conformation, which means it needs to be equatorial or axial. It needs to be axial, right? So we need to do a ring flip. So the first thing I would do is number the carbons 1, 2, 3, 4, 5, 6, right? So in a ring flip, carbon 2 comes down, carbon 5 comes up. So whatever was axial becomes equatorial. Whatever was equatorial becomes axial. But if you're up, you're always up, right? So this chlorine right now is pointed up, I would think. And it's equatorial. So so when I do a ring flip, it better be up and axial. Good. So you draw the other thing slanting the other way. So like you said, carbon 2 gets pulled down. It's right there. Carbon 5 gets pulled up. The headrest becomes the footrest. The footrest becomes the headrest. So this is now carbon 2. It'll be 1, 6, 5, 4, 3. So carbon 1 has the chlorine on it, right? And it should be pointed up. So this should be the chlorine, now axial. This ethyl group was pointed down, should be down and axial. There's an H. There's another H. So the question here is, what beta hydrogens are also axial and next to this chlorine? So normally, right, if you looked at this, you'd want to make the double bond between 1 and 2, right, because that'd be a more substituted alkene, right? But you can't because there is no hydrogen that's axial or trans to it, right? That's in an anti-periplanetary conformation. So there is a hydrogen, though, right, on carbon 6 pointed down. So the only place for it to do the elimination is between, right, it's taking the beta H from 6. Because even though there's a beta hydrogen on carbon 2, it's in the wrong position for elimination to take place. Do we see that elimination there? So it has to take the H on carbon 6. So the only product we can form then, the alkene has to be between carbons 6 and 1. So if carbon 2 we would have, let's see, number my carbons. 1, 2, 3, 4, 5, 6. So the new double bond is between carbon 1 and 2. New pi bond is there. Carbon 2 still has the ethyl group on it. And the H is right there. So let's do number 28. We'll do both parts. We'll do both parts. So this is a reminder of some alkyne chemistry, right? Remember we did the Glaser coupling, right? We could deprotonate terminal alkynes. Right, and to do that we needed, right, this H was slightly acidic, right, because it was sp hybridized with electrons in an sp orbital that's close to the nucleus, all that good stuff. Step 1, then we use a really strong base to deprotonate. And that gives us a carbanion, right? Pretty stabilized carbanion, right? Because the electrons are in sp orbital, which is close to the nucleus, which of course has a positive charge. Still reactive though. And then in the second step, what do? We added in an electrophile, right? Because this is a nucleophile now, right? And the electrophile we added in was alkyl halide. So this primary alkyl halide, so nucleophile, alkyl halide, just an SN2 reaction, right? So you've been doing these reactions for a while, right? We did these way back when. Right? You didn't know it was an SN2 then, but we did these, right? That was the way to add carbons. Remember the only ways you guys know how to add carbons? So that's a substitution, right? This is a SN2. Now in the other one, they go through the same first step, same strong base. So we're going from the same, we'll start from the same intermediate, right, the carbanion. But now instead what they put in there, instead of a primary alkyl halide, they put in this. Tertiary alkyl halide. So the question always is, what type of alkyl halide do we have? So here we have what? So can we do an SN2?
No.
So what's on the table still? So no SN2 for sure, but SN1, E1, and E2 are still on the table, right? So now let's look at what kind of nucleophile do we have. What kind of nucleophile do we have? Reactive or less reactive? Is there a negative charge? If it has a negative charge, what's it going to be? Reactive. If it has a full-on negative charge, it's going to be reactive. So that eliminates SN1 and E1, so what are we left with? E2. So then once you go to E2, what do you start looking for? Beta hydrogens. Okay, how many types of beta hydrogens does this molecule have? One. How many does it have? 9. Has 9 beta hydrogens in only one type. Right? If it was an NMR spectrum, how many peaks would this NMR have? How many peaks would this NMR have for this molecule? Just one. Just one big old peak. One. And what kind of splitting would it have? Would it be a singlet, doublet, triplet, quartet? It should be a singlet. Has no nearest neighbors. They're all the same. It's one peak, singlet. Right? Look back at your Friedel Crafts NMR. Think about those ones. Right? So beta hydrogens. Take the H. Take that down. So the product we get in this case would be, actually we recreate what? The starting material. Right? We remake the starting material. Right? Remake the starting material. And we'd also make a new alkene plus Br minus. But I don't think they don't want the Br minus.
They just want the starting material?
They want the, well, because that's what I made, right? I remade the starting material. Right? And I also made this alkene. So let's look at number 29. We start with this tertiary alcohol. And somehow it's going to go to this 3-membered ring, which we've seen before. It's an epoxide. We've seen the 3-membered ring before. It's an epoxide. All right. It's one of the things you were supposed to know how to do way back when. All right. So it's an epoxide. What do epoxides come from? What starting material? Well, there's no pi bonds left. So what if you had a guess, right? We've learned about what kind of functional groups. Alkenes, alkynes, right? Alkyl halides. So if there's no pi bonds left, there's probably only how many pi bonds to start with? 1. So this epoxide probably came from an alkene. Right? Maybe? Right? Could have came from that alkene. Now, could have this alkene have came from this alcohol? Yes, it could have. Right? We learned, right? We could turn alcohols into good leaving groups, couldn't we? Remember that? Right? If I used HCl, I could protonate that alcohol, make it leave. Right? You could protonate this, kick that over. Now we have a pretty good leaving group, right? Pretty good leaving group, right? We still have Cl minus floating around. Pretty good leaving group. Let it leave. Right, it's a tertiary alkyl X, whatever X could be, any leaving group, right? It doesn't have to be a halogen. All right. So what do we have left? A tertiary carbocation. Could we have the Cl take an H and make that? Yeah, we could. Right? We've done this with SN. We did an SN1 just like this in your quiz and also in your homework for chapter 9 with HI. Remember that? You start with an alcohol, turn into a, switch out the OH for an I. Similar to your quiz too. So now let's just do an elimination instead. And then the final step would be MCPBA, metachloropurbenzoic acid. It's just a way to turn an alkene into an epoxide. Now, this is not the way you can do it on sapling. This is one way. Right? This is one way. They hold you back because they give you they only give you so many reagents, right? So I do it this. I showed you this way because I want to emphasize the fact that, right, there is more than one way to do these. Oftentimes, right? Sometimes more efficient, less efficient, all those kind of things. So this is one way of analyzing this. Right? So there's two ways to make epoxides. The first way I just showed you, epoxides come from alkenes, right? There's another way to make epoxides. That's through an SN2 reaction. That's what I'm going to show you next. Okay, ready to do that? So we'll restart this whole We'll do 29 again. Right, because epoxides can come from two places. Epoxides could come from alkenes or they could come from an SN2 reaction. So now I'm going to show you what sapling kind of forces you into, right? Because they only give you certain reagents to choose from. But it also highlights that epoxides can come from two different sources. Okay. So, first step, have our epoxide. Let's number some carbons. 1, 2, 3, 4, 5, 6, 7. So just like we talked about today when we were talking about forming that ether, right? Because an epoxide is simply, at the end of the day, it's an ether, right? It's an oxygen bond to two carbons. It's an ether. And if we're going to form this from an SN2 reaction, we got to think about, right, which of these bonds to oxygen do we want to break? C2 or C3? Right? So remember what I told you, we talked about how do we pick? What's the most important part? What's the first question we always ask ourselves? What kind of alkyl halide? So if we have to do an SN2 reaction, do we want a tertiary alkyl halide, like it would be on carbon 2, or do we want a secondary one? Right. So let's break this bond. Right. So who's going to get the electrons? Oxygen is going to be O minus, and carbon 3 is going to be delta plus. How am I going to make carbon 3 delta plus? What would I do? Put what there? To make it delta plus, what could I put on there? If you want to make a carbon delta plus, what do you put on it? A halide, right? Just put a bromine on there. So we take one step back. Let's put a bromine on 3. And this can be that. Right? Oxygen still has the electron density. Carbon 3 is now delta plus. Right? Now if I want to add a bromine and an OH, where would that come from? What starting material would that come from? You guys should have seen that before. Where does that come from? What kind of starting material to add a bromine and an OH? It's Br2 and water is the reagent, but what starting material does it come from? An alkene, where does the double bond need to be? Between 2 and 3, right? All right. This alkene, right? Can we make that from this? What from the alcohol? Kind of the way I just showed you when I used HCl or H plus to do that E1 elimination. Remember that? So we can go from there. Now going forward. So number 32 deals with epoxides. So I'm going to talk more about epoxides on Wednesday, show you some more of these things. So our starting material is a terminal alkyne. And our final product is to what? What are the two things we made? What are their relationships to each other? What are these two things we've created? What are they to each other?
Enantiomers?
They're enantiomers. So I'm just going to draw one of the enantiomers. Good. They are indeed enantiomers. Okay. So plus enantiomer. Okay. So we need to work backwards. We need to work backwards. The hard part for this is you haven't recognized this product. Right? You've seen stuff that are trans, right? If you looked at this, the OH and the OH are trans to each other, right? So if you go back to that last problem we just did, we saw the BR and the OH were trans to each other, right? So we know we probably have to go through some sort, we're going to go through a carbocation if the things are always trans to each other. Carbocations make it so things can be trans and cis. So we know we don't go through a carbocation. If they're always right, carbocations, you'll get a mixture of everything. If you see something that's only trans, right, the enantiomer is also only trans, you should recognize no carbocations. Right? So we're going to not go through a carbocation, so probably going to go through some sort of three-member ring intermediate. So in this case, that three-member ring intermediate is an epoxide. So if you want to make a diol, two alcohols, you can do that with an epoxide. Oops. So an epoxide, remember again, it's a three-membered ring. We don't need to change anything else. HCH3. Right? Very similar to what? Looks like a bromonium ion would look, right? And if you had bromonium in water, a bromonium ion in water, right? The water would have came and attacked the carbon, right? So if we just want to add another OH, I'm just going to show you this right now. What you'd want to do is add in an OH minus. Right? Because the OH minus is just going to attack here, open this up, and you get the diol. You see that? You could also just add water too.
Would one react faster than the
OH minus would react faster, better nucleophile. It's like an SN2 reaction, right? This is like a leaving group, right? You can think of it that way as leaving group, right? Like bromonium ions are leaving groups, right? Does Br minus like to be in a three-membered ring? Well, no. Either does oxygen. Right? So you've seen leaving groups before too. You didn't realize it. You did. So everybody okay with this? Epoxide is a way to form diols. So we've already done this. Where do epoxides come from? What starting materials do epoxides come from? That's the reagent, right? The reagent is MCPBA, that's right. So remember, you gotta be very careful, right? This is a good point. Starting material is different than reagents. Reagents react with the starting material. What starting material does this come from? What kind of starting material? What functional group would this come from? Double bond, an alkene. That's right, it comes from an alkene. And the methyl and the ethyl on the same side, right? Do you see that? The methyl and the ethyl are on the same side, pointing out, pointing out. So we have a Z alkene, right? Two groups on the Z same side. How do we make a cis alkene, a Z alkene? What could that come from? What starting material could that come from? An alkyne. That's right. Make sure we number our carbons so we don't lose any here. 3, 4, 5. 1, 2, 3, 4, 5. Right? So now, right, we should recognize right away, when you see a terminal alkyne that has, how many carbons does this terminal alkyne have? 1, 2, 3, and all of a sudden we have how many carbons total? 5. One of the best ways you guys know to make carbon-carbon bonds is by deprotonating this, right, and doing an SN2 reaction. So that's one more step back, and we're there. And we're there. So in the forward sense, the first thing we need to do, right, is to deprotonate the alkyne. That's that NaNH2, right, makes the C minus. Then we need to add in the electrophile. And how many carbons do we need to add? So 2 carbon pieces, might as well heck throw a bromine on there. I want to take an alkyne and add 2 H's to it, but stop there. In a cis fashion, what do I need to do? What reagent's that? That's H2 and Lindlar's, good. Lin's catalyst, good. How do we make epoxides? That was that MCPBA, metachloroperbenzoic acid. And then I've already shown you the final step is just this O minus attacking and kicking down that. So NaOH and water will do that. So I think the reagent they use is, and they have it in water, so that's where the last H comes from. So, this is a problem. I'm going to introduce it first. So let's say you want to make an alkyne. Right? How do you make an alkyne? So, we haven't done this probably yet. But an alkyne has how many pi bonds? 2. What way do you guys know how to make pi bonds? Via what kind of reaction? Eliminations make pi bonds. So if you need to make 2 pi bonds, how many eliminations do you need to do? There you go. So you need to have how many leaving groups? 2. Okay. So 1, 2, 3, 4. So what if I told you if we had this and we treated it with strong base, we end up with an alkyne. We do 2 E2s essentially. Yep, really. Right, so I'll draw the mechanism out. Let's do that. And we already know what kind of alkenes do we like to make? Cis or trans alkenes, E or Z alkenes. We like to make E alkenes, right? We want to get things away from each other. So it doesn't matter which one I pick first here. All right, if I take that H, so the first step we're going to make an alkene. This bromine's still there. Take another H away. We end up with the alkyne. And we have 2 Br minuses floating around, and we made 2 NH3s, which are gases, which bubble up. So it's a double elimination to make an alkyne. So a double elimination to make an alkyne.
So should we just know that, or would there be like a hint, like?
I'm showing it to you right now.
That's,
How do you make alkynes? Through a double elimination. That's the way to make alkynes so far, is to do a double elimination. And then, what would that came from? To add 2 bromines, what would the starting material be if I wanted to add 2 bromines? How do we add 2 bromines? What's the starting material? Br2 is the reagent. What's the starting material? A what? alkene between 2 and 3, right? So this would be the starting material. 1, 2, 3, and 4. And this is very similar to number 31 in your homework. It starts with an alkene, and it wants you to make an alkyne. This is how you do it. So the reagents needed to go forward would be Br2, right, would add 2 bromines. And then a strong base, excess strong base, would do a double elimination, as shown here, give you an alkyne. So let's see a problem where we have 4 carbon piece going to this would be a cis alkene, right? A Z alkene. So that should tip us off maybe something about Lindlar's I would be thinking about, right? See that cis alkene. We start with 4 carbons, we end up with, let's see, 1, 2, 3, 4, 5, 6. So we added 2 carbons. I would say, let's call this carbon 3, 4, 5, and 6. Right, the reason I do that is because I know, right, the action is the pi bond, right? I'm assuming the stuff where things are happening is also happening here on the starting material. So one step back, we have a cis alkene that would have came from a alkyne. You should recognize that. Right? They would come from an alkyne. Right? Because that's the only way you know how to make cis alkenes is from alkynes. So this is one of those things where you got to go back and look at all those reaction sheets. Look at that reaction sheet again. Right? All that stuff still matters. It does not go away. Right? Now, I have an alkyne. Can I add carbons to an alkyne? Yep. So we know we need to do that, right? So let's do that. We need to add how many carbons? We need to add 2. So I would even say, right, if our numbering is correct, it would have came from this. And now here we have an alkyne, but did we start with an alkyne? Our starting material was not an alkyne. So we had to make this alkyne. How do we make alkynes? So how do we make alkynes? We have alkynes have how many pi bonds? 2. For every time we form a pi bond, we need a leaving group. So let's assume this came from this. All right, the dibromide. If I want to add 2 bromines, what would the starting material be for that? To add 2 bromines would be what? Br2 is the reagent. What's the starting material? An alkene. That alkene. So what reagents will we use? We'd use Br2. That would add the bromines at 3 and 4. If I want to do an elimination, I'd want to use Na, NH2, a strong base. And if I use a lot of it, I can do this all in one step. I could do the double elimination. I could also use it to take off this H, right? If this is step 1. Step 2, I could add in, right, the alkyl halide I want to add, 2 carbon piece. And then finally, if I want to turn an alkyne into a cis alkene, that's that H2 Lindlar's catalyst.